Today we are going to be continuing our discussion of conservation of energy. We're going to be specifically looking at springs. Springs are interesting not just because for their own sake, but also because a lot of things in physics and engineering end up getting approximated as springs. So like anytime you have a load-bearing beam, it's approximately a really stiff spring. Anytime you've got an atom vibrating in a molecule, it's attached by a spring to the other atoms. So springs end up being really important. I'd like to start by considering a spring onto which a mass has been attached. And so here's its rest position. We're on a surface that is frictionless. For the moment. So we're going to not consider friction. We're just going to say that it's on a surface so that we don't have to worry about whether the spring is also supporting the weight of the mass on the end, although we will get to that later. Oh, yes, sorry, I forgot I wasn't sharing my screen yet. Good catch, Trainmaster. So we'll say that this is the spring's natural length. So this is the point at which delta x is 0. Let's say that we stretch it out some distance and then just let it go and watch it vibrate. We can use energy to analyze how this thing oscillates back and forth. So let's consider a few different cases. So we'll divide these cases by how much stretch is in the spring. So we have some case here where we'll say that the stretch is equal to A, which is the maximum amount of stretch that the spring experiences. We'll call this point A. Point B will be the situation where the spring is at its natural length. And point C will be some arbitrary amount of stretch. All right, so what is the energy at each of these points? Or rather, what kinds of energy do we have? So someone tell me, what kind of energy do we have at point A? And as a quick recap, we'll note that we know about a few different kinds of energy. We know about kinetic energy. We know about gravitational potential energy. We know about spring potential energy. So of these three types, which of these types do we have at point A? Do we have any gravitational potential energy? So people notice we have spring energy. Yes, we absolutely do. Do we have any gravitational potential energy in any of these three cases? We got some no since they're horizontal, and that's part of that's partly true. I think it'd be more accurate to say that they do have gravitational potential energy, but for all three of them, it's the same amount of gravitational potential energy. So we can just go ahead and say that the height they're at is a height of 0. Um, so for the purposes of this analysis, the quantity of gravitational potential energy they have, we're defining to be 0. We'll say, all right. So at A, we have just spring potential energy, um, and we have no kinetic energy. So just spring. What about at B? What kind of energy do we have at B? Yeah, at B we have just kinetic energy. And what about at C? What kind of energy do we have at C? Yep, at C we've got both. So C is the most complicated of these three situations. So let's actually begin by analyzing A and B, but leaving C out. So between A and B, is there any external force acting on our spring mass system uh, at all in any of these cases? Right? Since our system is the spring and the mass, do we have any external forces coming in to mess up our analysis, to complicate things? It's very perceptive, Keys. The only time we have an external force is when we initially do work to stretch that spring out. But once we've stretched it, that's it. There's no external forces. So the work done from A to B as it oscillates is just 0. So like we stretch it out once, but then we let it go and voop, voop, it'll wiggle back and forth. And once we've stretched it and we let it go, there's no external forces doing work. But that means the change in energy from A to B is 0, which tells us that the energy at A is equal to the energy at B. Well, at A, we have just spring potential energy. So we have 1/2 K delta X squared. And at B, we have just kinetic energy. 1/2 mv squared. So if we know how much we pulled it back, or how much we stretched it by at A, so we can actually solve for how much velocity it must have at B. So the halves will cancel on both sides. Our delta x at point A is actually just A, the amplitude. So we'll have K a squared equals mv squared. Or we can say v is equal to square root of k over m times a. Everyone with me so far? All right. So this factor of radical k over m, we usually give this a special name, omega. And we'll see shortly that this actually is the same. It ends up having the same purpose as the omega in rads per second, the angular speed. So keep that in the back of your mind as we continue to do this analysis. So the next question we might ask is if A is the maximum stretch of the spring, what's going to be the maximum compression of the spring? Right, so the maximum stretch is A. What's our maximum compression? Anyone have an intuition? Minus A? Yeah, that's a really good guess. And if we call this point D, and this is point B and point A from our last page, we can easily show that the maximum stretch has got to be minus A, just by considering the energy at A and D. So no external forces means the energy at A equals the energy at D. So we have 1/2 Ka squared equals 1/2 K delta X squared. But that quickly just leaves us with A squared equals delta X squared, which means that either delta X is A, in which case points A and D are the same, which kind of ruins our analysis, or delta X is negative A. Everyone with me so far? So the next question I would like to ask is, how much time does it take to go from situation A to situation B? Can we use energetics to answer this question? Right? So we have a question about time. Can an energy analysis tell us about time? Josue, what do you think? Not sure? That's perfectly okay. Kelly John, how about you? You don't have to know for sure. What's your intuition say? Right? Because remember how we define how we the work energy theorem is defined. Right? Work is the integral of a force dot a distance. So in general, a conservation of energy analysis will not be able to tell us about time. It can tell us about distance because the change in energy is defined in terms of an integral over distance. But time, got nothing. Like the so we'll generally have to fall back on some other kind of analysis to tell us about time. Fortunately, we do have other modes of analysis. So we know about the energies of the springs, right, at A and B. What about the what about the forces? Do we know anything about the forces between A and B? Right? What's when we're between A and B, what force is the spring exerting on the mass? Right? So remember we have to remember back to last week when we talked about Hooke's law, right? So the force exerted by a spring is linearly proportional to how far it's been stretched or compressed, right? And it acts in the opposite direction of that stretch. So if you're stretching it out, then the spring is trying to pull the length back in. We call that tension. And if you have compacted the spring is trying to push its length back out. We call that compression. So between A and B, at any point, right, the force it experiences is going to be, right, negative k delta x, which means the acceleration between A and B is going to be minus k over m delta x. Is everyone with me there? I guess what formula is that? So this is Hooke's law, which we first encountered last week. And then from here to here, this is good old Newton's second law. Right, a force divided by a mass gives you an acceleration. So this gives us a kind of interesting equation, because on the left side here, this acceleration, well, that's dv dt, right? But on the right, over here I've taken the k over m and remembered that we defined square root of k over m as omega. So we have something involving distance on the right and time on the left. So this is maybe not going to give us what we want. Right? Because do we have the mathematical tools for doing for equating a time derivative and a space derivative at the same time? Right? I think maybe we're actually brave enough to try this. So let's take both sides of this and integrate from point A to point B. So on the right-hand side, we have a distance, right? Pull the minus omega squared out front because that's a constant. And for simplicity, let's say yeah, this is fine. We can integrate from the point where it is. So at point A, it's got a stretch of A. At point B, it's got a stretch of 0. Is everyone with me on that right-hand integral? Is anyone not with me on that right-hand integral? So I see some silence happening here. Okay. Well, I'm just going to press forward then. On the other side, we will be integrating with respect to time. We note that these cancel out, and at point A, our velocity is 0. At point B, our velocity is some quantity. So integrate dv, we get v, and evaluate it at 0 and some value v. So this is just our velocity. At the other end over here, we integrate over distance. So this didn't get us anything with respect to time, but we did recover the expression from the first slide, so that's at least comforting. If we do the analysis two different ways, we get the same answer, so that is nice. Let's ask this question a different way. What is the average velocity between A and B? Right? Because if we have the average velocity, we can we can get the time from A to B by taking the distance from A to B divided by the average velocity. Is everyone still with me?
Yes, but uh wouldn't the average velocity be dependent on like the acceleration, like the acceleration of the spring since it's giving a force to the block?
Well, yeah. So that's why we want that's why we're interested in the average, right? So it's going to be a different speed at A and at B. So we have to have some way of computing the average. And just as a reminder, our situation at A was a stretched spring. And our situation at B is an unstretched spring. Let's actually uh, answer this question by analyzing a third situation, which is somewhere in between. And I'm going to call this lowercase s here. So if we analyze the energy from A to C now, we still have no external forces, which means no work is getting done. So the energy at A has got to be equal to the energy at C. At A, we just have spring potential energy. And at C, we have both spring potential and kinetic energy. Okay. Let's cross off all the halves. And we can write down VC squared is equal to KA squared minus MS squared over M. Which again is going to give us omega squared A squared So, in one sense, it's easier to talk about the average v squared than it is to talk about the average v, right? Because v squared is going to go smoothly from 0 to like omega squared a squared as as delta x squared goes from a squared to 0. Does that make sense? Like we have two buckets that we can put the energy in. Our first bucket is spring potential energy, and our second bucket is kinetic energy. So every time we take a bit of energy out of the spring bucket, we put it in the kinetic bucket. So if we have, say, 4 bits of energy that we start out with, on average, how many bits of energy are going to be in the kinetic bucket? Anybody? Yeah, that's right. So on average, our kinetic bucket will be half full, and our spring bucket will be half full. So it's relatively easy then to write down what is the average v squared, right? The average v squared is when you have, right, half the original energy. Cruz, you ask why? Why to which part? Why is it 50-50? So when we think about the oscillation of the spring, right? The spring is not accelerating smoothly, right? Its acceleration starts out at a maximum where the spring is stretched at its maximum, and so the acceleration starts out high when the velocity is low, and then when the velocity is high, the acceleration is small because the spring is less stretched. So it's not smoothly accelerating. What it is doing is smoothly exchanging one kind of energy for another. Okay. So what we want is average velocity, but what it's easier to get is average energy. Does that make sense? Yep. Okay. Do we have any other like anything else that we want to any other questions that arise here? Okay. All right. So let's give ourselves a little room. And let's maybe rewrite this a little bit. So the average kinetic energy is equal to half the potential energy. And have you all seen angle brackets used this way? That sometimes we end up using angle brackets. So at the beginning of the semester, I used angle brackets for vector notation, but they also kind of confusingly get used as an average or expected value. Okay, so no questions. All right. So this is an example of something called the virial theorem, which we just stumbled across by accident as we were playing with the um, energy analysis of springs. Um, but in general, if you've got some sort of oscillation um, that has a kinetic and a potential component, the virial theorem says that the average kinetic energy is going to be n over 2 times the potential energy, where n is the exponent for the radial dependence of the potential. So here we have kx to the 1. So n is equal to 1. If you've got gravity, where the potential energy due to gravity well, now the exponent on the r is a minus 1. So for gravity, right, you get a minus 1 out. And then there are other so this is a very general theorem, but for us, we're just dealing with springs right now. So this n is going to be a 1. So the average kinetic energy is half the potential energy. Yeah, Jaden. So in this case, I'm using the angle brackets for average just because if I wrote T bar, I I'm weirded out by the way that looks. All right, but if our average kinetic energy is equal to 1/2 uh, Ka squared. No, these should be angled. Where is, or rather, at what amount of stretch is the spring potential energy half of its maximum? Right? So if the spring potential energy right? So the spring potential energy at, say, some point. Oh, I was using S, wasn't I? How big does SC need to be so that it has um, half of the kinetic energy that it did at the starting point? It's not halfway to the max distance, right? Because we're scaling quadratically. So if you're halfway to the max distance, you actually only have a quarter of the potential energy. So I'm going to cancel out the k and one of these halves here. So you have half the potential energy when you're a factor of square root of 2 away from the maximum distance. Right? And then if we don't like radicals in the denominator, we can get rid of it by saying 1 over radical 2 is the same as rad 2 over 2. Okay, so you actually have half the kinetic energy or half the potential energy when you are significantly further out than halfway. So if you have if this is the distance, this is the amount of stretch for half max potential, then this has also got to be the stretch where you've got half of your maximum kinetic energy, right? And we can use our previous analysis to say, well, then what is what is our speed when our kinetic energy is half of the maximum kinetic energy? Right, so our halves cancel off. We get a k over m again, which I'm going to write as omega squared. And then when we have square root of 2 over 2, squared, that just gives us, that's just a half. Right, so we get 2 over 4, which is a half. So square root of all of this. So it's 1 over square root of 2 omega a. So this is the speed when we have this is the speed that our mass is moving when its kinetic energy is half of the total energy budget. And so in some sense, this is the average speed of our mass on a spring. We have comments before we move on? Okay. Let's keep that, and I'm going to go back to using bar now because V bar looks just fine to me. So remember, our goal in finding this average speed was actually because we were interested in the amount of time that it would take. And we thought, well, we can get the time if we have the average speed, because then we'll just be able to say that the time it takes is going to be the distance that the mass travels divided by the average speed. And now we are definitely able to do this. So we have A over square root 2 over 2 omega A. A's cancel. So it's interesting that this factor of omega shows up in our calculation for time. Right? It doesn't matter how far we've stretched it. All that matters is that ratio between mass and spring constant, right? Which is what our omega is. Let's actually look at a um, slightly different presentation of this. What if we wanted to write down the position of the position of the mass on the end of our spring? So the position relative to the natural length of the spring as a function of time. I propose that we can actually write this down with a trigonometric function. How can we check whether this proposal meets what we already know about the motion of a spring? Right? We know from our previous analysis that if we let this spring oscillate, it's going to oscillate between a stretch of A and a compression of minus A. So this cosine function, what's the maximum and minimum distances that this cosine function can give us? Right? 0 to pi, you're on the way there, but someone who hasn't been talking a lot today, like Zachary, what is the biggest and smallest that a cosine function can be? Exactly. It can go from -1 to 1. So the biggest that this thing can be is A, and the minimum it can be is minus A. That checks out. Right? Because that's exactly what we expect for the stretch. If this is our position function, what's our velocity function? Calderon, how do we get a velocity function from a position function? Nothing? Anybody then? How do we get a velocity function from a position function? Yeah, we take the derivative. We differentiate the function. So v of t is going to be right the derivative of x of t with respect to t. Derivative of cosine is negative sine. And then we have to use the chain rule to take the derivative of the argument here. Derivative of omega t is just omega. So we get minus omega a sine of omega t. What's the maximum and minimum that our velocity can be? Right? What's the maximum and minimum that a sine function can be? Yep, it's negative 1 to 1, same as the cosine function. So what is the, if we go back, did we derive that bit yet? We did. So on the very first page, the velocity's maximum is square root of k over m times a. We called square root of k over m omega. So yeah, that checks out. The maximum velocity is in fact omega a, and that's what this function gives us. So are you convinced? Is anyone not convinced that this function serves the purpose that we need it to serve? Is anyone... How many people are just processing it and aren't ready to render a verdict yet? Yeah. Let's get one more piece of information. So here's Hooke's law. I'm going to neglect the delta for a moment. Force, what we mean by force is mass times acceleration, right? And of course, what we mean by acceleration, like we can write acceleration as the second derivative of position. So if we rewrite this this expression of Newton's second law and Hooke's law, we can write the second derivative of position with respect to time is equal to minus k over m times x. And of course, we're going to rewrite k over m as omega squared. So we have minus omega squared x. So basically, x has to be a function where when we take the second derivative, we get a negative sign, we get a constant squared, and we get the original function back. What kind of functions have those properties? Right? What kind of function has the property where if you take the second derivative, you get a negative constant times the original function? Anybody? You think of any function. Take the second derivative of, right? Think of, some function f such that the second derivative of the function is equal to the negative of the function. That's a good guess, Keys. Not quite parabolas, but it is something curvy. And I'll give you a hint. Yeah, there's only two functions that have this this property. It's just sine and cosine. So the only possible solutions here, right, are either x is a sine function or x is a cosine function. So when we're trying to solve problems of this type, we generally will write down that it's a sum of both, right? So could be a cosine function plus a sine function, in fact. Right? Any sum of cosine and sine functions will have this property that we need. Only one of them will have the property, though, that the initial position is equal to the amount we stretched it by. Right? So if our initial position needs to be just a, right? So plug in 0 for t, that actually gives you sine of 0, which is 0. We also have that the velocity at time 0 is 0, right? So if we take the derivative of this possible sum, we get minus a omega times sine of 0 plus b omega cosine of 0. And that tells us that b has to be 0. Right? Because the sine of 0 is 0, so this first term is 0. This second term is 0 only if b is 0. So the question as stated, right, just going from Hooke's law, actually has only one solution. Right? Our position as a function of time has to be a cosine. So it is not an accident that cosine omega t has the properties that we expect when we are analyzing a moving spring. And here, actually, it becomes much easier to talk about time. So now if we want to know, well, at what time, right? So we were originally interested in the time from A to B, well, which confusingly I've used A and B again here, but the time for it to go from max stretch to zero stretch. So at zero stretch, let's think about this, try and think about this in terms of our oscillating trig functions now. So a full cycle looks like this. We start at maximum stretch. We decrease down to zero stretch. Here's maximum compression. We come back up through zero stretch, and then we're at maximum stretch again. So if we want the time to go from maximum stretch to zero stretch, that's going to be 1/4 of the cycle. Now we're used to thinking of our trig functions as going from 0 to 2 pi. And that actually is a really useful way to think of this here, because this could be our theta equals 0, or it could be our stretch equals a maximum. And here, this could be stretch is a minimum, compression is a maximum, stretch is 0, and then stretch is a maximum. But it's also perfectly valid to say, well, if this is our theta equals 2 pi position, our maximum compression is going to happen at theta equals pi, and then here theta equals pi over 2, theta equals 3 pi over 2. So our question, asked all so long ago, is how long does it take to oscillate from maximum stretch to zero stretch? We can actually reframe that and ask, what is the time to go from theta equals 0 to theta equals pi over 2? Well, our theta is just the argument of our cosine function here. So if we want this entire argument to go from 0 to pi over 2, then that implies our time has gone from 0 to pi over 2 omega. All right.